All right, so our next section here, we've got substitution rule for definite integrals. So let's call this is 6.8. All right, so this starts off with looking at how we do a substitution. Remember that when we were doing some substitutions earlier, we had to think about this function, and we're going to call it u. Usually we call it u, and it ends up being we're undoing chain rule is what's happening here. So when we look to see when we've got some composite functions going on, the inner function is what we're going to call u. And if we kind of have a look at it and try to decide, okay, so if this is going to be our u, when I differentiate that, is that another piece of our integral here that's going to divide out? And so that often ends up being the case, that it's set up like that. So we are going to be able to divide some stuff out. So this rule says if u is g of x, then the integral of f of g of x times g prime of x. And we're going to call that instead, we're going to call that f at u du. Notice that we will need to change our limits of integration, and there's a couple of different ways that we can look at doing that. All right, so let's get at it. First example, we have the integral from 0 to 1 of this 6x minus 9 over 2 square root 2 minus 3x minus x squared all dx. Now, if we realize that I've got an inner function downstairs, I have this square root of 2 minus 3x minus x squared. That trinomial is your inner function. And if we let that be u, is 2 plus 3x minus x squared. Then our derivative of this, so whether we call it du dx, and we differentiate that, this ends up being 3 minus 2x. Often, we would just write it as our dx over here. It means the same. Du is equal to 3 minus 2x dx. And what we're going to be looking for is that represented here. And with a common factor of -3, it ends up being in there. And so really what we have is my integral of square root u is downstairs. And we have 6x minus 9, but if I common factor out a -3 from there, this ends up being common factoring out -3 gives me 3 minus 2x. This is still just dx, but notice that this is this, which is, so that's equal to du. So my integral ends up being -3 du over root u. So that's now in terms of u. We still need to look at what happens to 1 and 0 in terms of x. But remember that that's in terms of x. And so if we look at that and if we say if x is equal to 0, what happens to u? And we're going to look at this new equation that we've made. And if x is equal to 0, then u is equal to 2 plus 0 plus minus 0. So u is equal to 2, and if x is equal to 1, then u is equal to, and we do that calculation again, 2 plus 3 minus 1 ends up being 4. And so what we have there for is our 0 is replaced with 2, our 1 is replaced with 4. Be aware that which corresponds with which limit, because it won't necessarily just always be the larger one, it ends up being your upper limit. It has to be corresponding. The 1 is corresponding to 4, so that ends up being our upper limit, and the 0 corresponds to 2. All right, so this is now ready for us to go ahead and integrate. So this ends up being equal to -3. This is u to the -1/2. So let's call that u to the +1/2. And we're going to divide that by 1/2. So dividing by half is multiplying by 2. And this goes from 2 to 4. We end up with -6 root u from 2 to 4. So therefore, -6 root 4 plus 6 root 2, because we're subtracting. And this ends up being equal to -12 plus 6 root 2. Now, we could have gone at this a different way. We could have evaluated those limits of integration later on, like we could have finished up this question and done it that way. I'll show you what I mean by that in here. Question number 2. We have ln x over x dx. So our u is equal to ln x, and du is equal to 1 over x dx. So therefore, this ends up being equal to u du. Now our limits of integration, we don't quite know what that is. Let's go ahead with this integration first. And this one ends up being nice and easy. This is u squared over 2. And u squared over 2 ends up being equal to, well, u is ln x, so ln x over 2. Thing is back here we didn't know what this was in terms of u, but we do know that in terms of x, it just goes from 1 to 2. So we just kept our limits. Once we've done our substitution back, then this ends up being correct. And this ends up being, sorry, I'm missing the fact that this is ln x squared over 2. And we substitute this in. We end up with ln 2 squared over 2 minus ln 1 squared over 2, which ends up being ln 2 squared over 2 minus 0. That last part is equal to 0. So, like I'm saying, we could have at this point, we could have said when x is equal to 1, therefore this is ln 1 over 1, which is 0. And so that would be our lower bound. When x is equal to 2, this would be ln 2 over 2, and that would be our upper bound, and we would put those here in terms of u. This would be ln 2 over 2. This would be 0, and we could evaluate it that way, or we could keep it in terms of x and just pick up that 1 and that 2 afterwards. Either way is fine. And then number 3. E to the root x over root x dx from 1 to 9. So whatever we have as an inner function when we have composite functions. And so u is equal to root x. So we differentiate this. This ends up being du is equal to, this is x to the half. So we multiply this by a half, subtract 1 from our exponent. This is 1/2 x to the negative half dx. We should probably isolate part of that because we have dx over root x back here in our original equation. So let's call this 2 du, multiplying both sides by 2. And let's call this 2 du is equal to 1 over root x dx. And now we can do our substitution. This is e to the u. This is over root x times dx is now being replaced with 2 du. So e to the u times 2 du. We integrate that, and this is equal to 2e to the u. We have this unknown limit of differentiation here. And so this ends up being equal to 2e to the root x. But now we've changed it back into x. So this is going from 1 to 9. This ends up being 2e cubed minus 2e. And that is it. If you have any questions, please let me know, and we'll see you in the next one.